Hello everyone and welcome to this module on continuum mechanics. Today's topic is about right and left Cauchy-Green deformation tensors. We already get to know these tensors a bit, like we had C and we had B, if you remember. And we also have the Lagrangian strain tensor, or E star, if you remember. Okay, so in this module, we're going to dip into the right and left Cauchy tensor as well as the Lagrange strain tensor. We're going to find their diagonal as well as off-diagonal terms and see what they represent, because we know that we have so far we have developed different tools and different strain tensors, and now we discuss these three tensors, and then we pick our tools accordingly. So let's get to the first topic, which is the right Cauchy-Green deformation tensor. So if you recall from the previous session, we defined C equal to F transpose F, where F was the deformation tensor, and it was equal to U squared. C actually was equal to U squared, and this U was the pure stretching tensor. And remember that if U is equal to I, for example, so instead of U, you have I, then there is no deformation. It is totally obvious. So in order to find diagonals and off-diagonal terms of this C, this deformation tensor, we're going to develop the diagonals, develop some kind of relations in here. So for the diagonals, suppose that you have dx1, which is the element in the deform configuration, or in the current configuration. It is equal to ds1n, for example, and dx capital 1, d capital x1 is equal to d capital S1 E1 here. And here, you know that I use E1, E2, and E3. So this is the right-hand side orthogonal basis that we basically use in this course. So fundamentally, they are perpendicular to each other, these elements in the reference configuration. And you also know that dx is equal to f d capital X. So in order to find out this dx1 dot dx2, so I have for the diagonals, I have dx2 equal to dx1, and of course dx2, maybe I can write it here, is equal to, dx1 is equal to d capital X2. So what I have in here is dx1 dot dx2 is equal to, I have f dx1 dot f dx2. So this one, I can write it as dx1 f transpose. So this is dx1 dot f t transpose f dx2. And this is nothing but C. This is C. So this is dx1 dot C dx2. So I can write this as ds1. This is ds1 n dot ds1 n. So these are parallel. So this become ds1 squared is equal to, I have here ds capital 1 squared e1 dot c e1. Therefore, I can write c11 e1 dot c e1. This is c11. So this one is basically d small s1 squared divided by d capital S1 squared. Or you can write this as this simply whole squared. And we already discussed this, that's why this one is C11, because you have E1, the rest are 0, right? So I have 1 in here, and then you have dot, this is C1, the rest of components, and then finally you have 1 0 0. And what you get in here is basically C1 1, the other component, which is, for example, C2 1 and C3 1. The dot product is basically C1 1, because this one goes with this one, 0 with this one, 0 with this one. All right. Similarly, you can conclude that C22 is basically d small s2 divided by d capital S2 whole squared, and C33 is equal to d small s3 divided by d capital S3 whole squared. All right. There's something here that I would like to point out, as the book also mentioned. So the book said that, remember that we already mentioned that C is equal to U squared. But here, U, for example, U11 is not equal to the root of C11, except, or for example, U22 is not equal to C22, or C33 is not equal to U33 is not equal to the root of C33, except it is diagonal. So C is a diagonal tensor. So the rest are 0. If the rest of that, the C term is not diagonal, so here you have 1, for example, 0 0 1 0 0. This is not something that you can simply say that, okay, U is the square root of C. All right, so let's get to the non-diagonals, or off diagonals. So in the off diagonals, we have dx1 equal to d small s n, for example, and we have dx2 equal to ds2m here, because we don't know whether these two elements in the reference configuration, either whether they are perpendicular or orthogonal to each other, but we know that they are. We have d capital S E1. They are orthogonal in the reference configuration here. So here, we have E1 and E2. So initially they are perpendicular to each other, but in the current configuration, they are not necessarily perpendicular. Therefore, we can say that, okay, this angle, we call it beta, same as book. So I have, for example, n in here, and I have m in here. So the cosine, there is there is an angle between m and n. So if I want to find, for example, dx1 dot dx2 is equal to, so we already know that this is equal to f dx1 dot f dx2. This one can be written as dx1 f transpose dot f transpose f dx2. This is c, so we have dx1 dot c dx2. So here I have ds1 n dot ds2 m, which is equal to ds1. This is the blue one. Okay, write it with another color. So if I can also change this in here, this is this side of the equation. So I have this in here. So I have ds1, ds2, and n dot m can be written as ds1, ds2. So the dimension of m, the dimension of m, n and m times their the cosine between them. These are unit vectors, right? So this is 1, this is also 1. So we get ds1, ds1, and ds2 cosine beta. And remember here, they're small s. So we get to this side of the equation where we have this in here. So I have dx1 dot c dx2, which is equal to ds1 e1 dot c ds2 e2. So I can write this as ds1 ds2 e1 dot c e2. Now I have 1 and 2. So 1 is equal to 2. Therefore, I can write this as, this is nothing but C12, right? So C12 is equal to this d small s1, d s2 cosine beta divided by d capital S1, d capital S2. And remember here that our initial x1, capital X1 was ds E1 and dx2 was ds capital S2 E2. So you can see you can also write this for 1, 3, where you have ds1, ds3 divided by d capital S1, d capital S3. The cosine, for example, we can call this alpha. And this is, of course, for dx1 equal to ds1 e1, and this is dx2 equal to ds3 e3. And similarly, you can write this for c2, 3, ds2, ds3 divided by d capital S2, d capital S3, cosine gamma for d capital X1, d capital X2, ds2, e2, and d capital X3 is equal to ds3, e3. So if you look at the diagonals in here, you can see that only the length of the element is just changing. But here, in addition to the change in length, we can see that this angle or this direction is also changing. There is one more thing in here. So if we call this equation 3, so from 3 we can get something also really interesting. So we have C12 is equal to ds1 divided by ds1, d capital S1. We have d small s2, we have divided by d capital S2 cosine beta. This is nothing but square root of C11 times square root of C22 cosine beta. Therefore, you can write cosine beta as C12 divided by square root of C11 times C22. Let's get to the example 3.23.1. There are some important comments in here I would like to mention. So basically, there are 5 parts in this example. So it said that you have your displacement field in the form of small x1, capital X1 plus 2x2, and then x2 is equal to x2 and x3 is equal to x3. So in the first part, it says that obtain C. What is this tensor? So we know that C is equal to F transpose F, and for this we have to first calculate F. F is the gradient of x, and here we have the partial derivative of small x1 with respect to x1, x2 with respect to x2, and blah, blah, blah. All right, so here, using these equations here, we have 1, 2, 0, 0, 1, 0, 0, 0, 1. And C is, of course, equal to F transpose F. So if I transpose this 1, 1, 0, 0, 2, 1, 0, 2, 1, 0, 0, 0, 1 times 1, 2, 0, 0, 1, 0, 0, 0, 1 is equal to all right, so we have 1, 2, 0, 2, 5, and then 0, 0, 0, 1. Then the second part says that what are the eigenvalues and eigenvectors. So from here, you know that one of the eigenvalues is 1, and of course the eigenvector is you can find it because it is the third one. So one of the lambdas is 1, and for example n3 is e3. So it could be, for example, n1 e1. It's not important. So this is lambda 1, but could also be this is n1, for example, e3, but here we're going to call it n3 equal to e3. So and here you have 1, 2, 2, 5. So this becomes very, very easy to handle. So the determinant of this becomes 1 minus lambda times 5 minus lambda minus 4 is equal to 0. So from here you get 2 lambdas, lambda 1 and lambda 2, and you can find the corresponding eigenvectors. So here you get something like lambda 1 equal to 5.8, n1 is equal to 0.4 e1 plus 0.9 e2 plus 0 e3. Okay, I'm not going to write it. So lambda 2 becomes 0.2, n2 is equal to 0.9 e1 minus 0.4 e2. You can also use maple or something like that. And you have lambda 3 equal to 1, and we have n3 equal to e3. So the third part actually wants you to obtain U and U inverse with respect to the principal directions. And these principal directions here, remember that these are in the deform configuration, right? So if you write in here U, you have, this is the first principal value or eigenvalue. This is the second, 0.2, and this is 1, right? Sorry, this is C. So in terms of principal values, you have C like this, and you know C is equal to U squared. Therefore, U is nothing but square root of 5.8, square root of 0.2, square root of 1, which is 1. And the rest of are 0. And U inverse, since we have a diagonal, let's say diagonal tensor, so you have 1 divided by 5.8, you only need to divide 1 by the diagonals in here, so you have 1 divided by 0.2, 1 by 1 is 0, so the rest are 0. And remember that these are with respect to the principal directions. So with respect to principal directions or eigenvectors. Then the book says, find U and U inverse with respect to EI, or the reference configuration. So if you remember from the first module, we had a transformation. We said that if you have U in the current configuration, or let's say U prime is equal to Q transpose U Q, where U is second order tensor. So here, if you have U in the current configuration, it is equal to Q transpose U Q. And here we would like to find E with respect to EI in the reference configuration. Therefore, this is U in the reference configuration. So if you say this Q comes in here, so you have a Q here, so this becomes I, and you have a Q transpose here and Q transpose in here, so this becomes I. So this finally becomes U reference. Q is equal to, so Q U current is equal to, sorry, Q transpose is equal to U ref. So this is Q transpose Q. Here you have two important equations which we learned from the first module. And now we want this U reference or UEI. This is nothing but in the reference configuration. So U in the reference configuration is equal to, so I have my first let's write Q. So if you remember, we fill in the orthogonal tensor vertically. So I have my n1 here, n2 in here, and n3 in here, like this. I have to fill it in like this. So I have n1, 0.4, 0.9, 0.4, 0.9, and then 0. And then 2 is 0.9, and then minus 0.4, 0.9 minus 0.4, and then I have 0. Here I have E3, so it is 1, and the rest are 0. So according to this, so Q in EI or reference configuration, sorry, U is equal to Q Q, then U, Q transpose. This is U in current configuration. From part, let's say, C, is basically here. This U C in here. This is part C. So I have to put this in here. So I have 0.4, 0.9, 0, 0.9, minus 0.4, 0, 0, 0, 1. Then I have 5, square root of 5.8. Square root of 5.8, square root of 0.2, and then 1. And then I have Q transpose in here. So 0.4, 0.9, 0, 0.9, minus 0.4, 0, 0, 0, 1. So this will give you U. You can simply calculate this. And then you have U inverse EI. This is the same in here. So you have Q, then you have U inverse from part C, Q transpose. So if I just copy this, paste it in here. All right, so I just need to replace this with U inverse 5.8, 1, whatever, square root of 0.2, and here I have 1. So then you have U inverse EI. The last part of the example says that find R in the reference configuration, again EI. And if you recall, we had F equal to RU. So F U inverse is equal to RU U inverse. This is I, and this become R. But here, since I'm going to find R in EI, so in the reference configuration, I need F, and I need U inverse in EI, or reference configuration. So I have F, which is 1, 2, 0, 0, 1, 0, 0, 0, 1, if I remember correctly. 1, 2, the rest correct. All right, then I have this U inverse in here, which I copy from the book. So I have 1.2 minus 0.70 minus 0.7, 0.7, 0, 0, 0, 1. And finally, you can get this orthogonal tensor in here. All right, next we have example 3.23.2. And here you have this displacement field in here. In the book, basically the question asks you to find the stretch in part A in direction of stretch in direction of E1. So to find the stretch in direction of E1, we first need to find C, and C is nothing but F transpose F, where F is the del X and is equal to here 1K 0, 0, 1, 0, 0, 0, 1. Therefore, C is equal to 1 double 0 in here, K 1, 0, 0, 0, 1. And this is F transpose, so I have K and here I have this one. So if I do this, I get 1, I get k, I get 0, I get k in here, I get k squared plus 1, I get 0, 0, 0, 1. This is C. So if you want to get the stretch in E1, so you get something like E1 is 1, 0, 0 dot. Then you have C, which is 1, k, 0, k squared plus 1, 0, 0, 0, 1. This is C11. This is E dot C E1, right? It's 1, 0, 0. So this one is 0, 1, 1 dot. So this is 1, k, 0, which finally gives you 1. So you can also get this from, you already said that C11 is equal to ds1 divided by d capital S1. So here it becomes squared, it becomes 1. Part B is similar to part A. So I'm going to go for part C, where it says that, okay, find the stretch in the direction. So again, a stretch in direction E1 plus E2. So in this direction, we have 1, 1, 0. And remember here that you have 1 and 1, and these are unit vectors. So 1 divided by a square root of 2, because this is 1 divided by square root of 2, E1, plus 1 divided by square root of E2. So if you write it in the unit basis, then, so if I just bring this bit down, perfect. So then I have dots and I have C vector, C tensor. So copy and then paste it in here. And then I have 1 divided by square root of 2, 1, 1, 0. So I put this in here. So this square root vanishes. And I can get this in here. So I get something like 1 divided by 2, 1, 1, 0 dot. So I get 1 plus k. Then I have k plus k squared plus 1. Then I get 0. So this becomes 1 divided by 2 times 1 plus k plus k plus k squared plus 1, which becomes, this is 2k plus k squared plus 2. So this becomes k squared divided by 2 plus k plus 1. And remember here that this is d s divided by d capital S squared. The 4 ds divided by d capital S is the root, square root of this expression in here. So this is k squared divided by 2 plus k plus 1. And the book also asked for the angle between the directions E1 and E2. So if you remember from here, we derived this equation here. We said that cosine beta is equal to C12 divided by square root of C1 and square root of C22. So cosine beta is C12 divided by square root of C11 and times square root of C22. So C12 here is, this is C12, this is K, C11, and this is C22. So it is K divided by a square root of 1, which is 1. Then I have a square root of K squared plus 1, which is the square root of C22. All right, next we have example 3.23.3. And in this example, we have part A, where it says that the eigenvalues, the eigenvectors, find the eigenvectors and eigenvalues of C. It's better to write it this way: eigenvectors and eigenvalues of tensor C. Let's find them out. All right, so we know that U is the pure Stressian tensor. Un is equal to lambda n. So you can write it here. Un is equal to lambda n. This is the definition of the eigenvalues and of eigenvectors. So you have lambda as eigenvalues and n as eigenvectors. And we know that C is equal to U squared. So using these two, I can write this U squared n is equal to lambda U lambda n, which I can write as lambda because lambda is a scalar, U n in here. And this is nothing but C, this U squared. So this C n is equal to lambda un. This un is basically lambda n. So lambda squared n. Therefore, eigenvalues of C are lambda squared if eigenvalues of U are lambda, and eigenvectors of C are n if eigenvectors of U are n. This is also an important kind of conclusion here. All right. So part B says that if n, says that if n is a principal direction of C, so becomes the principal direction of C. So the deformed state, in the deformed state, an element is in the direction of Rn. Deformed state so if n is the principal direction in the deformed state, an element is in the direction of Rn. Of Rn. So here it says that if you have an element in the reference configuration where it was in the principal direction of n, where n is a principal which is in the direction of n, where n is a principal direction of C, then in the deformed state, that element becomes in the direction of Rn. And to prove this, we can simply write, so you know that your element is in the reference configuration. Your element is d capital X, so it is ds, and it is in n, which is a principal direction of C, right? And you know that you're in the deform configuration, you have d small x is equal to fd capital X. So from here, you can write d small x is equal to f, instead of d capital X, all right, dsn. And here I have ds, so I can just take it out in here, ds f n, and instead of f, I'm going to write ru, so f is equal to ru. So I have ds ru n. And if you remember here, we had un equal to lambda n. So un was equal to lambda n. Therefore, this becomes dn. I put also lambda in here, and then I have rn. So you see that if you have an element that was in this direction, n, where n is a principal direction of C, then in the deformed configuration, it becomes in this direction, Rn, with this eigenvalue, It's the eigenvalue, and this is the eigenvector. All right. Now, let's get to the Lagrangian strength tensor. We already get to know this E star bit, where it basically included a linear part and a nonlinear part. Where in the infinitesimal strength tensor, we basically neglected this nonlinear part and we only had this linear part in here. Now we're going to discuss this E-star, or the Lagrangian strength tensor, and using this E-star, we're going to formulate the large deformation strength tensor. All right, so if you recall from our previous modules, we had dx equal to f dx, and from here we basically concluded that 2e star plus I was equal to C, the right Cauchy tensor, strength tensor, because this f was basically del u, the displacement gradient, plus I, and then we had f transpose f, which was equal to C, and then we found out this, we got this, let's say, del U plus I transpose del U plus I, and then from here we got this equation here where this E star was equal to an expression like something that was something like, if I recall correctly, it was 1 divided by 2 del U plus del U transpose plus half of del U transpose tell you. It was something like this. It is not important. You can just get this equation from the book. But the whole point was that I didn't just bring this equation out of my hat. So we already derived this equation here. All right, so from here, I can write that E star is equal to basically half of C minus I, where C is the right Cauchy-Green tensor and I is the identity tensor. And of course, if C is equal to I have no deformation, so E star is equal to 0. So in order to find the diagonals and off-diagonals of this tensor in here, so I start with diagonals. So similar to tensor C, we start with dx1 is equal to, for example, ds1n. And here I have d capital X1 is equal to d capital S1, and this is E1. So in reference configuration, I also have dx2 equal to ds2 E2. So they are in the reference configuration, they are basically perpendicular. All right, with this in mind, I have dx1 dot dx2, and here I assume that dx2 is equal to dx1. Therefore, I have dx1 dot dx2 because I'm going to calculate the diagonals in here. I have equal to, if you remember, it was dx1 dot c d capital X2. So we already had this equation here. We already derived it. It's in here. So from here, d small x1 dot d small x2 is equal to d capital X1 dot c dx2. So maybe we can call this the black equation. So from black equation, it's black equation, and then we have the black triangle. We have dx1 dot, so instead of writing C in here, so I can write C as 2e star plus I, right? So I have 2e star plus I dx2. So I have dx1 dot dx2 is equal to, and remember, these are just elements. These are not exponent. So I have dx1, I put 2 in here, e star dx2 plus dx1 dot I dx2, which is basically dx2. So I get dx1 dx2 minus dx1 dot dx2 is equal to 2 d capital X1 dot e star d capital X2. And here, if I have dx1 equal to dx2, then this becomes ds1 squared, because we have ds1n dot ds1n minus this becomes ds1 capital S1 squared is equal to ds1 squared, and this is e1 dot e star e1, and this is nothing but e11, e star 11. So e star 11 is equal to ds1 squared minus ds1 squared divided by 2 ds1 squared. And if you just compare this with with E11 with the infinitesimal strain tensor, it was ds1 minus d capital S1 divided by ds1. So if you see here, you get a better result. It's a quadratic kind of, equation, and you get better results. And you can simply write E22 star as ds2 squared minus ds capital S2 squared divided by 2 ds squared and E33. But remember here that here it is for dx1 ds1 e1, and here dx1 was simply ds1, and we didn't know that it is in direction of e1 or whatever. We are not sure about this, but we know that it is in the reference configuration, it is in the direction of e1. So here we can write that it is for dx2 equal to ds2 e2, and dx2 d small x2 is equal to ds2, for example, m in here. All right, and you can write e, for example, 3, 3. You sort 3, 3 in here. Next, let's go to the off diagonals. For the off diagonals, we follow the same procedure here. So I have dx1 dot dx2 is equal to, minus d capital X1 dot d capital X2 is equal to 2 times dx1 dot e star dx2. And here we have d small x1 is equal to ds1 n, and we have dx2 d small x2 is equal to d small s2 m, and we have here dx1 is equal to d capital S1 e1, and dx2 is equal to ds2 e2. Remember here in the reference configuration, e1 and e2, they are perpendicular, but in the reference in the current configuration, they are not necessarily perpendicular. So if this is n, this is m, there is an angle between them. But here in the reference configuration, they're perpendicular to each other. Therefore, the dot product here is 0. So here we have dx1, so this becomes ds1 ds2 n dot m, where we write it as n m cosine beta. These are unit vectors, so their dimension is 1. So I have cosine beta in here is equal to, this is 0, this is 2 ds1 ds2, and this is e1 dot e star e2, and this is e star 1 2. Therefore e star 1 2 is equal to ds1 ds2 divided by 2 ds1 ds2 cosine beta. Or you can put this 2 in here and you can write it like this. Remember, for dx1 equal to ds1 e1 and dx2 is equal to ds2 e2. These are perpendicular to each other, but this dx in the reference configuration, but in the current configuration, they are not perpendicular necessarily. So this is x2, this is ds2 and m. So you already learned that, let me just switch my color, that E star is equal to 1 divided by 2 C minus I. And this C was F transpose F minus I. and we know that F is equal to del U plus I. Therefore, we can write E star as 1 divided by 2 del U plus del U transpose plus half of del U transpose del U. And in additional notation, so we have E star ij, so it's a second order tensor. We have half of, we can write this as a partial derivative of ui with respect to capital Xj, because we are writing everything with respect to the current configuration, plus partial derivative, this is transpose, so we switched we swapped the indices here, so partial derivative of uj with respect to xi plus half of, here I write del u transpose, and here I have del u. And remember, here you have to get something like Tij, something like a second order tensor, where this term has the same indices in here. So you have two free indices here. You have ij in here. And to get this, let me just switch my color so you can get it better. So this Tij is basically del u transpose, which is basically del u. Let me write it like this. So you have I m transpose del u mj. So finally what you get is a second order tensor Tij. So if this is transpose, so you get del u mi, then you have del u mj. So that's why we write this as, partial derivative of um with respect to xi times partial derivative of m with respect to xj. So that's why we get this equation here. Partial derivative of um with respect to xi times the partial derivative of um with respect to capital Xj. This is the linear part. And this is the non-linear part. We already had this in the infinitesimal strain tensor, but incorporating the nonlinear part actually gives us a better estimation of this strain tensor in here, the Lagrangian strain tensor. The examples here are also really easy. So if you follow, if you've followed the examples in the previous section for the right Cauchy-Green tensor, you definitely are able to answer these examples, to solve these examples, and without any problem. So next, get to the left Cauchy-Green tensor. This is tensor B, and we already said the importance of this B because it is it is frame independent, and we're going to utilize this B in later calculations for the stresses and elasticity. All right. So we already mentioned that B is equal to VR. This is F equal to VR, and we already mentioned that B is equal to V squared. And we already proved that B is equal to F transpose. This B tensor is also called B is also known as finger deformation tensor. There are some relation between there are some relations between B and C which where we can derive in here. So correlation between B and C. So you know that B is equal to F transpose, and basically F can be written as RU in terms of RU, and this is RU. So we have U transpose R, and U transpose, since it is a stretching tensor and it's a symmetric tensor, so U is equal to U transpose. So this becomes RU squared R, where U squared is basically C. So this is R transpose RC R transpose. So this is one equation here. This is one. And you can also write this C is equal to F transpose F. So F in terms of V and R is VR transpose, and you have VR. So it is equal to R transpose V R transpose, and V is also symmetric. So V R transpose V squared R. This V squared is B. So R transpose B R is equal to C. This is also another important equation in here. So now let's get to the components of B. But first, we need to find the principal directions of B in the reference configuration. We already said that the reference in example in here, example, I think it was the last example in part C. Yes. The unit vectors of C are the same as U, but let's see what are the principal directions of B in the reference configuration. So we have UN, so principal directions and values of B. So let me just change this color to blue. All right. So the principal directions, so UN was equal to lambda n, if you remember. And for C, actually, from here, we got Cn is equal to lambda squared n. And C is nothing but, let's call this 4 maybe. So from 4, we can write R transpose B R is equal to lambda squared n. And from here, I can write R transpose B R n is equal to lambda squared R n. And this is I, so I remove this. So BRn is equal to lambda squared Rn. So here you can see that Rn is the unit, is the eigenvector of B, and lambda squared is the eigenvector of B. So we can rewrite this expression in here for B. So if I copy this and paste it in here, so if I delete this, okay, let me see if I can get it. Okay, great. So the eigenvalues of B are lambda squared if eigenvalues of U are lambda, and eigenvalues of B are Rn, and maybe I can write this with another color, if eigenvalues of U are N. Okay. So with this in mind, we're going to find the diagonals and then off diagonals of B. So let me see. All right. So if you have Rn in here, in the deform configuration, you have N in, let's say, of U. These are the eigenvectors of U. But let us consider, for example, you have dx, d capital X, in the reference configuration as dsn. So here you can get n as, E1, for example. So if n is equal to E1 in here, and for B, this is basically Rn. So in order to get this Rn in here, you have to, this is Rn, this is E1, right? Because we said that the eigenvectors of B are Rn. For C, it wasn't a problem because the eigenvectors of N, they were the same as N in the deform configuration. But here for B, these are Rn. So Rn is equal to E1. So to get rid of this R on the left-hand side, we have to just multiply it by R transpose. So we have R transpose in here. So this becomes I. So N is now R transpose E1. So that's why we write here N, where N is equal to R transpose E1 in here. All right. So again, from from this black square, we have dx1 times dx2, where dx1 is equal to, let me write, so dx2 is equal to dx1. So from here, from the black square, we have dx1 dot dx2 is equal to d capital X1 dot c d capital X2. All right, where I have dx1 is equal to ds1n, right? All right, so I have ds1 squared is equal to, because I have n dot n, which is 1, is equal to ds1 squared is equal to ds1, and then I have n, which is R transpose E1 dot C, and then I have dx2, which is the same as dx1. So here d capital X1 is equal to dx2. So I have here ds1 R transpose E1 again. So I have ds1 squared is equal to d capital S1 squared times R transpose E1 dot C R transpose E1. And I can write this as E1 R dot C, sorry, R dot RC. This I can write as R transpose E1. So I have RC R transpose, RC R transpose is nothing but B. So from 5 I can write this as ds1 squared E1 dot, this is B, B E1. So therefore I have ds1, this is nothing but B11. So I can write B11 is equal to ds1 squared divided by ds1 squared, or the whole squared. This is the same as B, but remember here, for dx equal to this, this ds, where n is this one. So I have ds 1 R transpose E1. And B22 is ds2 divided by d capital S2 squared, or dx, which is initially in ds2 R transpose E2, because we said that this is the eigenvector of Rn. So we have to first use this eigenvector in here for the reference configuration, from the reference configuration. And then we have B33. So let's go for the off diagonals. For the off diagonals, we follow the same procedure where dx1 is ds1n, so we don't know its unit vector. It's totally arbitrary. dx2 is equal to ds2m, for example. So they have an angle. So this is n, for example, and this is m. They are not necessarily perpendicular, but we have dx1, which is ds1n, where this n is basically ds1 R transpose E1, and dx2 is basically ds2 m ds2 R transpose E2, for example. So dx1 dot dx2 is equal to d capital X1 dot C dx2, where we get ds1 ds2 then n dot m, where we get this as cosine beta is equal to, then we have this ds1 ds2, then we have E1 R, so we have R transpose E1, so I write it as E1 dots R, then I have C R transpose E2, which is B, this is E2, and this is nothing but this is B12, which is ds1 ds2 all small divided by d capital S1 d capital S2 cosine beta, where this beta is the angle between n and m. And remember, here we made an assumption for dx1 equal to, here, ds1 R transpose E1, and dx equal to, dx2, sorry, have to put this in superscripts. dx2 is equal to ds2 r transpose e2. You can do the same for b1 3 and b2 3. Remember here that initially R transpose E1 and R transpose E2 are orthogonal or perpendicular. They are perpendicular. So if this is R transpose E1, this is R transpose E2. The most important thing in here is that the initial vectors here for B, for the left Cauchy-Green deformation tensor, are R transpose E1 and R transpose E2. So if we write B basically in tensorial form, we have FF transpose, which is equal to I plus del U times I plus del U transpose. So this becomes I transpose plus del U transpose. I transpose is the same as I, so I have del U in here. So I have I plus del U transpose plus del U plus del U now del U transpose. So B is equal to this expression here. And if I write it in indicial notation, I have Bij is equal to delta Ij, which is I plus del U transpose. So it is partial derivative of Ui with respect to xj, so it is transpose. Therefore, it is j, and this is I, plus del U, partial derivative of Ui with respect to xj, plus, and here, again, we have something like no, this is Tij, and this Tij is equal to del U transpose is equal to del U. So I have Im and I have del U mj transpose. So this is basically del U Im. This becomes del U j m. Therefore, if I write this in indicial notation, I have U, partial derivative of Ui with respect to xm, times partial derivative of xj with respect to, U j with respect to xm. So if I just write it down here, so partial derivative of Ui with respect to xm times partial derivative of Uj with respect to xm. All right. And also remember, for infinitesimal strain, or deformation here, we have E, or 2E, is equal to, 2E plus I is equal to, maybe write it like this. So 2E plus I is equal to B. Similar to C is equal to 2E plus I, or I can write it like this. So from here, you can conclude that for infinitesimal deformation tensor, basically C and B are equal. So the most important thing about the left Cauchy-Green tensor is that you have to find R transpose EI in the reference configuration, And remember that when you plug it into dx equal to d small x equal to f d capital X, this x is basically ds r transpose e, for example, e1, e2, e3. And you basically have this e1 and e2, and then you have to rotate it with respect to with this orthogonal tensor r, with r transpose e1, for example, here, and r transpose e2, and then you find dx. This is very, very important. So if you have f, you can just plug it into this equation e1 and find it. So you can't use ds e1 in here. You have to use ds r transpose e1. All right, so these are this is the last topic that I would like to talk about.